In this video, I want to talk about continuity and differentiability. So what's the basic idea behind continuity? Let's start with that. So let me give you a graphical example. So looking at this graph, would you say it's continuous or discontinuous on the interval from A to B? As you can see, there's no breaks, there's no jumps. This graph connects from A to B. There's no missing points. So we could say that f of x is a continuous function from A to B. Now, what are some examples of functions that are not continuous? So let's call this A, B, and C. So on the interval from A to C, notice that we have a jump discontinuity. As you can see, there is no connection between the left part of the graph and the right part of the graph. Therefore, this is a discontinuous function. It's not continuous. Now, there are some other types of discontinuities that you need to be familiar with. So this type of discontinuity at point C is known as a hole. So that's a type of removable discontinuity. The jump discontinuity is a non-removable discontinuity. And another one you need to be familiar with is the infinite discontinuity, which usually occurs at a vertical asymptote. As you can see, this side goes all the way up to positive infinity, and this side goes down to negative infinity. So for example, let's say if you have a rational function like 1 over x minus 2. X cannot equal 2 because this function will be undefined. You'll have a 0 in the denominator. And so you're going to have a vertical asymptote at x equals 2. And that's going to be a point of discontinuity. So anytime you have a vertical asymptote, it's discontinuous at that point. So those are some examples of functions that are not continuous. Now, what about differentiability? What's the main idea behind that? Continuity tells us if the original function f of x, if it's continuous or discontinuous at some point. Differentiability tells us if the first derivative, if it's continuous or not. So differentiability describes the continuity of the first derivative function. So let me give you some examples, some graphical examples where a function may be continuous but not differentiable. But let's look at our first example. So we said this is a continuous function from A to B. There's no breaks in the graph. Now, notice that the curve is smooth everywhere from A to B. There's no sharp turns. When you see that, that means that it's differentiable everywhere. The slope doesn't change erratically. Anytime you see a smooth graph, that means it's differentiable everywhere in this function. So that means that the first derivative, f prime of x, where this is f of x, is continuous on the interval from A to B. Now let's move on to our next example. And let's focus on this function, the absolute value of x. So the graph is basically the shape of a V. So notice that this function is continuous. We don't have any holes, no jump discontinuities or infinite discontinuities. So f of x is continuous everywhere on the interval from negative infinity to infinity. But now, is it differentiable? Notice that we have a sharp turn at x equals 0. The slope changes instantly from negative 1 to 1. So what is the slope at this point? There is no slope at that point. So that means that it's not differentiable at x equals 0, which means that the first derivative is not continuous at x equals 0. Now what we're going to do is we're going to break this function into a piecewise function. So on the right side we have the graph of positive x, and the left side is negative x. So it's x when x is greater than 0, and negative x when x is less than 0. And when x is equal to 0, the y value of this function is 0. So we could describe the absolute value of x using this piecewise function. Now what about f prime of x? We know that the derivative of positive x is 1, and the derivative of negative x is negative 1. But what about at x equals 0? What's the slope? So we can clearly see that the slope of the right side is equal to 1, and the slope on the left side is negative 1. And so if we plot f prime of x, we're going to get a graph that looks like this. So here's 1 and negative 1. So on the right side, where x is greater than 0, the slope is going to be 1, and it's always 1, so we're going to have a horizontal line. And for the left side, the slope is negative 1. Now, we don't know what the slope is at 0. Looking at this V-shaped graph, the slope changes instantaneously from negative 1 to 1. It doesn't go through negative 0.5, negative 0.2, 0, or 0.3. It just changed instantaneously from negative 1 to 1. So that means that we really don't have a derivative value at this point. So it's not differentiable. So we don't know what this is at x equals 0. We can't really say that the derivative of 0 is 0. We know that it is, but looking at the graph, we don't have a slope of 0 at this point. A slope of 0 will be a horizontal line, and this doesn't look like a horizontal line at x equals 0. So we can't really put a number here. Therefore, we can say that it's not differentiable at x equals 0, because we don't have a derivative value at that point, and we can see that f prime of x, it's not continuous at x equals 0. So differentiability describes the continuity of the first derivative function. Now, what I like to do at this point is give you some practice problems. Consider the piecewise function f of x, which is x squared when x is less than 0, and x plus 2 when x is equal to or greater than 0. Is the function continuous at x equals 0, and is it differentiable at x equals 0? So how can we find the answer to that question? Feel free to pause the video and try it. So let's talk about the continuity first. In order for a function to be continuous, we need to make sure that the left side and the right side of limits are equal to each other at 0. So what is the limit as x approaches 0 from the left? To the left of 0, we need to use this portion of the piecewise function. So that's going to be 0 squared, and that's 0. Now what about the right side of 0? The limit as x approaches 0 from the right. So we need to use this part of the function. And so it's going to be 0 plus 2, which is 2. So notice that the left side and the right side, they don't equal to each other. Which means that the limit as x approaches 0 from either side, it does not exist. So if the limit doesn't exist, you don't have a continuous function. And if the function is not continuous at x equals 0, it's automatically not differentiable at x equals 0. Now let's go ahead and graph the piecewise function so we could see that the function is clearly not continuous at x equals 0. So I'm going to graph these two separately at first. So y equals x squared is a parabola that opens upward, and so it looks like this. And y equals x plus 2, it's a linear function, so it's a straight line. The y-intercept is 2, and the slope is 1. So we have the point 0, 2, and with a slope of 1, there's a 1 in front of the x. You need to go 1 to the right and then up 1 to get the next point. So the next point is going to be at 1, 3, and then 2, 4, and so we have this straight line. Now, to put these two together, we need to use x squared only for the left side of 0. So we're going to use just this portion of the graph. And then we're going to use the right side of this graph. Now let's focus on this graph, x squared. So x is less than 0, which means that we're going to have an open circle at 0, and then it's going to go towards the right like that. And then here we have a closed circle because it includes 0. So if we plug in 0 into x plus 2, you're going to get 2. So let's say 2 is over here, and then it's going to go up with a slope of 1. So it's going to go up at a 45-degree angle. And as you can see, it's clearly not a continuous function. We have a jump discontinuity at x equals 0. So if the y values are not the same, it will not be continuous. So a quick test for continuity is to plug in these values into these functions. So if you plug in 0 into x squared, you're going to get 0. If you plug in 0 here, you're going to get 2. Because the y values are different at this x value, it will not be a continuous function. Now, let's talk about differentiability. So we know that if it's not continuous, it's not differentiable. And looking at the slopes, you can see the slopes are clearly different. The slope for this graph is 1, and the slope at this region, it looks like a horizontal tangent, so the slope is 0. If the slopes are not the same, it's not going to be differentiable. So we don't have to find the first derivative because if it's not continuous, it's automatically not differentiable. Now let's move on to our next example. So let's say that f of x is equal to x when x is less than or equal to 1, and it's equal to x cubed when x is greater than 1. So let's determine the continuity of this piecewise function first. So let's evaluate the limit as x approaches 1 from the left side. So we need to use x. So if we plug in 1 into x, that's going to be just 1. And then for the right side, we need to use x cubed. So that's going to be 1 to the third power, which is 1. So notice that the left side and the right side limits, they're the same. So that tells us that the limit as x approaches 1 from either side exists. It's equal to 1. Now we need to make sure the function is defined at 1, because if these two limits exist and if the function is equal to a value other than 1, you can get this situation. You can get a hole with a point above the hole or below the hole, and that would be a removable discontinuity. But this is a good first step for the function to being continuous. So what is the value of f of 1? X is equal to 1 in this region because this is less than or equal to 1. So that's just going to be 1. So we can say that the limit as x approaches 1 of f of x is equal to f of 1. This is the 3-step continuity test. So we could say that the function is indeed continuous at x equals 1. So what about the differentiability of the function? Is the first derivative continuous at x equals 1? We have to find out. It may or may not be continuous. So let's determine if it is. So let's start with f prime of x. And the derivative of x is 1. And the derivative of x cubed using the power rule is 3x squared. So what is the limit as x approaches 1 on the left side for f prime of x. So we need to use this, and so that's equal to 1. And the limit as x approaches 1 from the right for f prime of x, we need to use 3x squared. So that's going to be 3 times 1 squared, which is 3. So notice that the left-sided limit and the right-sided limit are not the same. So therefore, that tells us that the first derivative is not continuous at x equals 1. Which means that f of x, the original function, is not differentiable at x equals 1. So let's summarize what we have for this problem. The original function is continuous at x equals 1, but the original function is not differentiable at x equals 1 because the first derivative, f prime of x, is not continuous at x equals 1. So keep this in mind. Differentiability describes the continuity of the first derivative. Now let's go ahead and graph the piecewise function so we could see the answer visually. So on the right side, we have the graph of x cubed. So when x is 1, y is 1. And so this graph is just going to increase like that. If you were to draw the whole graph, it would look something like this. So we only need this portion of the graph. Let me draw that better. It's just going to go up. Now, this graph, y equals x, is just a straight line at a 45-degree angle. Well, that really doesn't look like a 45-degree angle, so let me do that again. So it looks something like that. Now, when x is 1, y is 1, so we don't need an open circle at this point. So as you can see, the graph is continuous. There's no disconnects, there's no jump discontinuities or holes in this graph. So the function f of x is continuous everywhere in this graph. Now, looking at the first derivative, it's not technically smooth. My drawing doesn't show it too well, so I'm going to draw it better. I think you could see the sharp turn. It's not really smooth at this point. So the slope of this line is 1, and the slope of this curve just beyond 1 is approximately 3. So the slope changes from 1, and then it instantly changes to a higher value, 3. So it's not really smooth at this point. And you could see it better if you use a graphing calculator to graph this piecewise function. But graphing it by hand, you could see that the slope changes abruptly at 1. It's not a smooth transition, which means that f of x is not differentiable at x equals 1. Now let's move on to our next example. So let's say that f of x is x squared minus 3 when x is less than 2, and it's 4x minus 7 when x is equal to or greater than 2. So is the function continuous at x equals 2? Well, let's find out. So let's evaluate the limit as x approaches 2 from the left. So we need to use this part of the piecewise function. So it's going to be 2 squared minus 3. So that's 4 minus 3, which is 1. So this is the 3-step continuity test. Now let's evaluate the limit on the right side of 2. So we have to use 4x minus 7. So that's going to be 4 times 2 minus 7. 4 times 2 is 8. 8 minus 7 is 1. So the left-sided and the right-sided limits are the same. So therefore, the limit exists. The limit as x approaches 2 from either side of f of x is going to be 1 as well. Now, we need to make sure the function is defined. So let's determine f of 2. So x equals 2 in this part of the function. So that's going to be 4 times 2 minus 7, which is 1 as well. So we can say that the limit as x approaches 2 of f of x is indeed equal to f of 2. Now once you make this statement, you've completed the 3-step continuity test. So we could say that the function is continuous at x equals 2. Now, is the function differentiable at x equals 2? So let's begin by finding the first derivative, f prime of x. So the derivative of x squared is 2x, and the derivative of the constant negative 3 is 0. The derivative of 4x is 4. So in order to determine if f of x is differentiable, we need to analyze the continuity of the first derivative. So we're going to use the 3-step continuity test on the first derivative function. So the limit as x approaches 2 from the left side of f prime of x, that's 2 times 2, which is 4. And the limit as x approaches 2 from the right side of f prime of x, it's simply 4. So because these two are the same, the limit exists. So the limit as x approaches 2 from either side of f prime of x is 4. Now we need to make sure that f prime of x is defined at 2. So we have to use this part of the piecewise function, that's 4 as well. And so we can make the statement that the limit as x approaches 2 for f prime of x is indeed equal to f prime of 2. So what this tells us is that the first derivative, f prime of x, is continuous at x equals 2, which means the original function, f of x, is differentiable at x equals 2. Now, as we said before, differentiability describes the continuity of the first derivative. So now let's graph the piecewise function. Let's graph each part separately, and then we could combine it into a single graph. So we have x squared minus 3, so the graph is going to be shifted down 3 units, and it's going to open in the upward direction. Now for the second one, it's 4x minus 7. So it's going to start at negative 7, and then the slope is 4. So as we travel 1 to the right, it's going to go up 4. So the first point is going to be at 0, negative 7, and then it's going to be 1, negative 3, and then 2, 1. And so this graph is going to look like this. So we need to combine these two into a single graph. So we're going to use this graph up to x equals 2, and then this graph beyond x equals 2. So let's start with this one. If we plug in 2, it's going to be 2 squared minus 3, so that's 1. Now keep in mind it connects at 2, so I don't need to put an open circle, because if I plug in 2 here, it will give me 1 as well. Now if we plug in 0, we're going to get negative 3. This should be 2, 1. I put the wrong point. And if I were to plug in 1, it will be 1 minus 3, which is negative 2. And there's going to be symmetry at x equals 0. So this graph is going to look something like this. Now, this one is going to be a straight line. So the next point if we plug in 2, if we plug in 3, it's going to be 4 times 3, which is 12 minus 7, that's 5. So it's going to be up here. So I'm going to draw that in blue. Now, we can see that the function is continuous everywhere. My graph is not perfect, but there's no holes or discontinuities in this graph. Now, looking at this point, x equals 2, notice that there's a smooth transition between the red line and the blue line. Because it's smooth, that means that it's differentiable at x equals 2. So the slope for that part of the piecewise function, the derivative was 2x. If you plug in 2, that gives you a slope of 4. And the derivative of this is just 4. So to the left of this point, like if you go just a little to the left, the slope is 4. And a little to the right, the slope is 4. So at this point, the derivative value at x equals 2 is 4. So because the first derivative is continuous, the function is differentiable at x equals 2. So I hope these examples help you to understand the difference between continuity and differentiability. Continuity is for f of x. It determines if f of x is continuous. Differentiability tells you if f prime of x is continuous or not. So make sure you understand that concept. Now, there are some other functions that you need to be familiar with, and that's x to the 1/3 and x to the 2/3. Now, even though they're different, there's some similarities between these two graphs. X to the 1/3 looks like this. And then if we graph x to the 2/3, this side looks similar. And this side is going to be flipped over the x-axis. Because of the square part of x to the 2/3, it's going to be an even function. It's going to be symmetrical. You could think of this as x to the 1/3 squared, or the cube root of x and then squared. So that's an even function. Now, for both of these functions, they're continuous, but they're not differentiable at x equals 0. Now, this graph looks smooth. However, at 0, it has a vertical tangent when you get very close to 0. My graph is not perfect, but it should look more like this. So at the center, you have a vertical tangent. Now, you know that the slope of a horizontal line is basically 0. Now, what about the slope of a vertical line? It's something over 0. Let's use 1 to keep things simple. So if you have 1 over 0, it's undefined. And when you have an undefined slope, typically you have a vertical tangent. And so it's not differentiable at that point because you don't have a derivative value at that point. Even though this looks smooth, when you have a vertical tangent, it tells you that it may not be differentiable at that point. Now, looking at this graph, the slope changes from a negative value to a positive value almost instantaneously at this point. Here, the function is going down, so the slope is negative. And then the function is going up, so the slope is positive. And so it's not going to be differentiable because we have a sharp turn. And at the same time, if you look at this curve, it's turning into a vertical tangent. And the same is true for the right side. It looks like a vertical tangent. Now, the fact that it's not differentiable at this point tells us that the first derivative is not continuous. Now, what type of discontinuity are we dealing with in the first derivative? When you see a vertical tangent, think of a vertical asymptote. When the function has a vertical asymptote, you have an infinite discontinuity. So if you see a vertical tangent, that tells us that the first derivative has a vertical asymptote at that point. And let's show that. So let's start with this function, f of x is equal to x to the 1/3. And let's find the first derivative. So using the power rule, it's going to be 1/3, and then x 1/3 minus 1, that's 1/3 minus 3/3, which is negative 2/3. And so you can rewrite it like this. If you bring the x to the denominator, it's going to change from negative 2/3 to positive 2/3, and we can put the 3 in the bottom. So notice that x is in the bottom of the fraction. And so that tells us that x cannot equal 0 for the first derivative function. But for the original function, it can. 0 to the 1/3 is just 0. And so that's why it's continuous at 0. But for the first derivative, if we plug in 0, it's going to be 1/3 times 0, and that is undefined. So if you were to graph this, there would be a vertical asymptote at x equals 0. So for this type of function, it's continuous everywhere, but it's not differentiable at x equals 0, because for the graph of f of x, there's a vertical tangent, and for the graph of f prime of x, there's a vertical asymptote, which means it has an infinite discontinuity, and so it's discontinuous at x equals 0. So remember, the differentiability of f of x describes the continuity of f prime of x. So if f prime of x is not continuous at a certain point, f of x is not differentiable at that point. Now let's look at the other example. F of x is equal to x raised to the 2/3. So using the power rule, it's going to be 2/3 x 2/3 minus 1 is negative 1/3. So once again, x will be in the denominator. So therefore, x cannot equal to 0. If we were to graph it, there's going to be a vertical asymptote at 0, which means that f prime of x is not continuous at x equals 0, which means that f of x is not differentiable at x equals 0. So anytime you see some sort of vertical tangent, there's a good chance that it will not be differentiable at the center of that vertical tangent.